So, we saw how you design the GMC compensator. So, we need two transconductors, because with one transconductor the problem was that it does not work for higher beta values, or if beta is closer to 1, then your pole will cancel the 0, and so second 0 will not be effective. So, we have to add the second 0 by using this GM and RC, high pass RC filter, and we have to push the pole due to this high pass RC filter outside UGB, because we do not want that pole inside UGB, otherwise it will reduce your phase margin. Okay. So, feed so, if you remember, your loop gain was proportional to V in by Vm for op-amp RC compensator, and this is proportional to beta V in by Vm for GMC compensator, which means if your line voltage changes, so line voltage is nothing but V in actually. So, higher line voltage means higher gain. So, what would happen? So, let us say you have designed your compensator for V in, for one particular V in, let us say 1.8 volt or so, and if your V in goes to 2.5 volt, what would happen? Or let us say 3.6 volt, 2x of that. So, what will change? Omega UGB will be shifted at 2x, okay, and the phase margin, let us say 60 degree or 55 degrees you have designed at, let us say 100 kilohertz, okay. So, and your UGB has shifted, so 200 kilohertz, I mean if you remember, your phase was dropping, okay, it was curvature kind of a behavior. So, if you remember, this was phase was looking something like this, okay, this was your omega UGB. Okay. So, if let us say this remains flat for a larger range of frequencies, then I mean 2x you may still see a good phase margin, but that is not necessary actually. It depends how the shape of your phase is looking at, phase response. So, what would happen? So, at 2x you might see a lower phase margin, it is quite possible, maybe 5 or 10 degrees less, and then if you on top of that you add, you know, there are some tolerances in L and C, and then other tolerances might be coming from your on chip compensation also. It will have some variation across process voltage and temperature. So, your phase margin may degrade even more than 10 degrees, by more than 10 degrees, and you do not want phase margin looking like 45 degrees also, okay. So, your 55 or 60 degree may look like 45 degrees, which is bad actually. So, what you want actually, if once you have designed it for 100 kilohertz UGB, you want your UGB around that only. If you reduce it, then what would happen? Your transient response will be bad, because your loop will not respond to any load transient or line transient, and if you increase, then and keep the phase response same, then your phase margin will reduce. So how can we compensate this? So we have to reduce or eliminate the effect of this V in. How can we cancel the effect of it? Yeah, so V in Vm if you derive from V in, then they will cancel out. Okay. So if Vm is proportional to V in, then Lg is only proportional to beta. Okay. For GMC compensator. So, and beta will only change if you change the output voltage, otherwise beta will not change. So, for a fixed output voltage, you will not see any variation when your input supply is changing. So, let us see how you do it. Zero to Vm, and let us say Vm equal to some k times of Vn. Okay. So, how do we design this ramp generator, sawtooth generator? Any idea? How can we do it? Integrate what? So, if you integrate, you will get a triangular waveform, not the sawtooth. If you integrate a square wave, you will get the dual edge modulation. Okay. But this is single edge modulation. So, let us say I call it I ramp. C ramp. This is edge detector, and edge detector is nothing but this. Okay. So, this is your clock signal and this is your edge. Okay. So, what would happen? Just apply the formula capacitor charging. What will be this voltage V ramp? I ramp. So, if this is TSW, divided by C. Okay. And this is nothing but what? Vm. Now, if I make I ramp equal to V in over what? Let us say some R. Okay. So, what would happen? Let us V ramp equal to V in into by R C. So, TSW, R and C constant. So, V ramp is proportional to V. Okay, or Vm is proportional to Vn. Let us not call it, let us just call it Vm only. This is the amplitude, and V ramp is the actual ramp signal. So, this is your V ramp. And this is your Vm. Okay. And what will be this period? What will be the period? TSW. So, what you do, you reset at every edge of your clock cycle, which is at a switching frequency. So, capacitor will discharge to 0, and then when this switch turns on again, turns off again, the capacitor will start charging, and the voltage, the peak voltage of this ramp will depend upon the current capacitor value, okay, and the period. So, for op amp compensator, it is fine, op amp RC compensator. All you need to do, just use this particular feed forward compensation. But for GMC, how do we do that? You have another factor, beta. Beta is not constant. Beta is constant if V out is not changing. Okay. But usually you do not design for a fixed voltage. These converters are supposed to be designed for wide range of output voltages. So, input output both is changing. Okay. So, for GMC compensator, LG is proportional to V in over Vm and beta, which is nothing but V in over Vm into, what is beta? Vref over V out. And what is V in over V out? What is this? D? 1 by D. Okay. Vref over. So, now in this case, will this work or not? If I make it a function of V in, so here I know Vref is constant, and if I make Vm also constant, so I have to make my loop gain a function of 1 over D. Okay, so LG is, so now assume if Vref and Vm are constant, then LG is inversely proportional to duty cycle, which means at high duty cycle reduces. So, I have to increase it in order to compensate. How can I do that? So, one possibility is you can do it digitally. Okay, you measure the duty cycle, you have a on time and off time. Okay, measure it with a high frequency clock, how many cycles of high frequency clock you get in one particular on time or off time, and from there you can use that code to control your proportional gain. Okay. Proportional gain will be your, you can change GM or you can change R. Okay. So that's the one way. What could be other way if I want to do it in an analog way? So let's say this is a GMC integrator. I will call it GMI. So one side is your, if this is your VREF, this is your VFB, and this was your V control, correct? This is CI. So what is KI? GMI by CI. And if you have a proportional component, let's say resistor, then GM by RP will be your proportional. So if I modify this, let's say I put a switch. And this is controlled by your PWM. What will be KI? Can you tell? D times? Okay. So your loop gain will be proportional to D, and here you have an inversely proportional to D, so they will get cancelled out. So the effect of duty cycle will be 0 in your loop gain. Okay. So there will be no effect as such. But this clock has to be high frequency. Okay. So one thing you have to make sure that this should not cause a ripple at the output. So if it's only integrator, so most likely even if you use a lower frequency clock, means the same clock which is coming from PWM, you may not see a ripple here, but it's only capacitor. But once you have a resistor here, then you may have a problem. Okay, every time you turn on and off, you will see a change in the proportional component, and that will get reflected into your V control. So this is your V control. So which means this PWM, and I want to retain the duty cycle but run this clock, let's say I want to run it, let's say 10 times of FSW. How can I do that? So we need to convert PWM, the same duty, we have to convert the same duty cycle into higher frequency. Okay. So let's say I have a V control. And this is your V ramp. This will give me duty cycle. Okay. So this is your PWM. Now let us say this is the period of this ramp is TSW. Now if I take another ramp, and the period of this, let us say TSW by 10, I can do that. And if I have a same control voltage, what will it do? It will simply change the frequency but retain the duty cycle. Okay. So you get PWM with same D. Okay. So this is the one way you can do it. But if you have only integrator, then you may not need to do all these things and you can directly, because here the the capacitor, you need to filter out this ripple. So this is your GM, VFP, VREF, CI, RP. So if you remember, we need a small cap here. So if I call it CP, this will have a pole at 1 over RPCP, and that is outside your UGB, and it will be closer to your switching frequency actually. This is high frequency pole, and if you want your ripple to be suppressed with this CP, then you have to keep this switching frequency, the PWM switching frequency, much higher. Okay. The frequency basically which is you are modulating your GM with. Okay. So this PWM frequency will modulate your GM in order to compensate for the variation in loop gain due to duty cycle. Okay. So that is why choosing a higher frequency would be better, so that you can get all the ripples filtered out at that frequency, and the only ripple left will be at your switching frequency here. Okay. There is one more advantage with this. Can anybody tell? This line, feed forward line component. Not this one, because here we are not controlling the duty cycle with the line. We are not changing the ramp signal, but in this case we are doing that in that op-amp RC, this particular thing. Can anybody tell the advantage of this, using this? Yeah. So if your line voltage changes, it will directly, your duty cycle will immediately change. Okay. Otherwise, it has to rely on the loop, the bandwidth actually, loop bandwidth, and which may be slower. Obviously, it will be 1/10 of your switching frequency. Here, even if there are any fast changes in V in, those changes will get reflected in your duty cycle and it will not change your output. So line transient is very good actually for this. So let me show you the example for line. So let us say this is your VDD. VDD is nothing but your line voltage. Let us say this is 1.8 volt, and all of a sudden it changes to, let us say, 3.6. So what duty cycle you expect? If it changes to 3.6, for a, V out is D times V in. So let us say V in equal to 1.8 volt and V out equal to, let us say, 0.2 9 volt. So forget about the losses here. Okay. So what will be the duty cycle? 0.5. Okay. For Vin equal to 3.6, D is 0.25, which means you have to go from 0.5 to 0.25, and duty cycle can only be changed by changing the control voltage. So it has to go through the entire feedback. Your control voltage will take some time to go from 0.5 to 0.25. But what is happening here? You are changing the ramp signal. When you are changing the ramp signal, you are completely bypassing the compensator, because this is ramp signal is after your compensator. So let us say this was 0 to 1 volt and your V control was 0.5 volt at V in equal to 1.8, correct? So what would happen to this ramp when it goes 3.6? We are making it proportional to V, na? So it should go to 2 volt. If it goes to 2 volt, then what would happen? At 0.5, what duty cycle you will get? 25%. So directly you will get the duty cycle, because your ramp. So whenever you change this voltage, the ramp. So let us say your line signal has changed here, okay, and that will get reflected immediately in your current, and the slope will change. Slope of this ramp will change, and it will try to charge to 2 volt instead of 1 volt when V in is increasing, increase to 3.6 volt. So your period will remain same, but since current has become 2x, so it will charge to 2x, or you can say your slope will be changed. So this is your VCTRL and this is 2 volt. So D equal to 0.5 here, D equal to 0.25. Okay. So that's what happens, which means any sudden change in line will not change your output voltage. So your line transit will be good here. Any question?
How it changes, how the magnitude itself be correct? The VRAM peak to peak, the peak value, how will it change?
No, you have increased the current. Huh? The charging current is increased. Your C is fixed, TSW is fixed. If I make this IRAM 2x, what will be the VM? It was going 1 volt, it will go to 2 volt now. So your capacitor is charging faster now. Huh?
How will the IRAM be controlled? From where it will be controlled?
No, where will be controlled means?
Like how will it be to things?
No, you have to design a current reference which will be function of Vn. So one way to design your current reference is this. Huh? Let us say this is Vn. What is this current? That's it. Okay, if this is W by L, this is also W by L. If you want some scaling factor, you can do that also. If you want some scaling factor, you have to simply RA, RB, V in or VDD, same thing. Okay, you can directly take VDD, or you can provide some scaling factor with this resistor divider and feed that. Okay, this is nothing but V to I converter. So, in this case IRAM becomes into, you have this RB over RA plus RB, this factor will also come. Okay.